Okay, so these notes are going to be on fluid friction. Fluid friction is a type of friction. We talked earlier about the idea that there was surface friction, and that was friction between two solid objects, and then the other kind is fluid friction. Most of the time we're going to think of fluid friction as just being air resistance. There's an actual equation that describes what the mechanism for fluid friction is. We're not going to look at the equation, but I do want you to conceptually understand what fluid friction depends on. So we're going to look at the factors that fluid friction depends on. So one of the factors that it depends on is the surface area. So the bigger the surface area of an object, the more resistance there is. And that's because physically there's more molecules that are in the way. So we'll say bigger surface area equals more friction. And this kind of makes sense, the idea like the flying squirrel or a parachute. The moment it like fans out, there's more molecules that are not hitting that fluid, so there's going to be more resistance. The other thing it depends on is the velocity of the object. And if you've ever been a passenger in the car and you have your hand out the window and the car is going, and the faster the car goes and your hand goes up and then it goes down and then it goes up and then it goes down, that's the idea that the increase of velocity is going to have a higher air resistance. So again, bigger velocity equals more friction. And the reason for that is just the sheer fact that from Newton's third law, for every action there's an equal and opposite reaction. So if your hand has a bigger velocity, your hand is hitting those air molecules harder, and so those air molecules are going to be hitting back harder as well. And then the third thing it depends on is the type of fluid. If I have a higher density fluid, I'm going to have more resistance. And if you think about just the difference between like air versus water, water's got a higher density value, and so water actually provides more friction when you're moving through it than the air does. And this applies even just different density values of air. Higher up in altitude, the air is thinner and it's less dense, and so there's less air resistance. And this is one of the reasons why airplanes are going to fly at a higher altitude, so they're not encountering as much air resistance when they're flying. So the one thing that kind of goes on, or that goes with this idea of fluid friction, is this idea of terminal velocity. And terminal velocity is when the air resistance equals the weight of the object. And when that occurs, there's no longer a net force, and so there's no longer an acceleration. So I want to kind of diagram this out for you. So imagine you have somebody, they're kind of big. We're going to call him Bronco because he's going to appear later on your worksheet. And we have Bronco's friend, Slim Jim. So we have Big Bronco and Slim Jim. Now, Big Bronco has a pretty big weight, so we'll say that his weight arrow is, I don't know, like 1,000 newtons. And Slim Jim, he's pretty tiny. He only has, I don't know, like 500 newtons. So when they first start going skydiving, let's say, and for now, let's just pretend that they have the exact same surface area, like Slim Jim has a fat suit on and Big Bronco's got a skinny suit on. Let's not worry about surface area. So they go out skydiving, and they step out of the airplane. And initially, they have initial velocity of 0. And then they begin to speed up. And as they speed up, they encounter air resistance. And their air resistance is going to increase as their velocity increases. So let's say for the first second, they're going 10 meters per second. They have a certain amount of resistance. Another second later, they're now going 20 meters per second. And the velocity increases, so the air resistance increases. These markers are terrible. And as their velocity increases, their resistance increases. Well, let's say 4 seconds into this, when Slim Jim's resistance is equal to 500 newtons, he has an upward 500 newtons and a downward 500 newtons. And so that means that the net force of 500 minus 500 is equal to 0. So there's no longer an acceleration. So Slim Jim has reached his terminal velocity. But Bronco, there's an upward resistance of 500 and a downward of 1,000. They're not balanced. So he's going to keep on increasing his velocity. So he's going to go higher and go faster and faster until until his resistance is 1,000. And when his resistance is 1,000, then it will balance out with his weight, and that's when he reaches his terminal velocity. So terminal velocity is definitely dependent on how massive you are. And one of the best examples is the idea of an ant. So you have ants all around sometimes, and you go and flick it off. And because of its like amazing exoskeleton, you flick the ant, and it goes in the air, and it just lands and it just kind of moves along. And the reason is, if you think about an ant has such a small mass, it has such a small terminal velocity. So the moment you flick it, you actually increase its speed to something much larger than the terminal velocity it can handle. So there's, in that case with like the ant, here's the ant, you have increased its speed so much, so it has this huge velocity, it has this huge resistance, and it doesn't weigh very, oh, I should do this vertically. You've flicked it, and it has this huge amount of resistance, and it has this teeny little weight. So actually, like you flick it to like maybe 1 meter per second, it will actually slow down. The resistance on it is so big, it will slow down until it reaches a terminal velocity that matches its weight, which is probably like, I don't know, 0.1 meter per second, and then it lands, and for it to go from 0.1 meter per second to 0 is so little that it just kind of tootles along. If you, on the other hand, were flicked and got to that huge velocity, you probably wouldn't have reached your terminal velocity, and so it would be, or even if when you do reach terminal velocity, to go from that terminal velocity value to a 0 value is such a huge acceleration, there'd be a lot more damage done. Okay.